Alright guys, you're welcome to the next deep learning papers. Today we shall be looking at this deep learning paper, deep compression, compressing deep neural networks with pruning, trained quantization and Huffman coding. And this paper happens to be the best paper in the ICRR 2016 conference. So what's the idea behind this paper? Well, if you look at the paper review series, you will discover that we also talked about another paper on the winning ticket hypothesis, which is also on the topic of how we can prune a network. So this work is also in the same direction of network pruning. In fact, this work was published before the winning ticket hypothesis. The winning ticket hypothesis was published just last year, 2019. So what is this work saying? It says that we can prune a network in such a way that we remove the redundancy in the weights, and the motivation is we want to be able to prune the network so that we can have a reduced storage, a reduced requirement for storing the size of a network of our trained model. So he also proposed the trained quantization, which means we can actually, even after we have pruned the network, we can further reduce the size of the number of bytes in our network by quantizing the weights. And we can also go ahead and use Huffman coding to further reduce the number of bits that we need to represent the pruned, the quantized network, so that we use less bits to represent more frequent weights. That's the idea. That's just what the network of what the paper is all about. Very simple but efficient approach. So, and they discovered that we can do a lot of pruning in the network by over 35 times to 49 times without affecting the accuracy. And each stage gives us a certain number of reduction in pruning. For instance, VGG19 can be pruned from whoopee sum of 552 MB to 11.3 MB. That's a lot, and that will make this to be able to port the models onto mobile devices, say like mobile phones, self-driving cars, drones, and the likes. So that is the motivation of that of this work. So let's look at the pipeline. So there are essentially three stages. You have the pruning, the quantization, and the Huffman encoding. The pruning gives us less number of weights. After pruning, you have less number of weights. For instance, in AlexNet, I think you have like 16 million parameters. So how many parameters? Well, so you can reduce the number of parameters in that network after pruning. The quantization, the output of that is to make sure we use less bits per weight. So we just decided to this approach, as we'll see soon, allows us to be able to use less number of bits per weight. Instead of using 32 bits floating point, we can use something like we can compress that with the code books and all of that. We can have less number of bits to represent our weight. And Huffman coding further helps. Even when we have less number of bits per weight, we can still like do a frequency count of our number of weights and use less bits for the more frequent ones and use more bits for the less frequent ones. That's just what they say. So the original network with the original size, you have trained the connectivity, you prune the connections, You retrain the weight. It's an iterative process. You prune, you retrain, you prune, you reiterate until you reach the original network accuracy. So by doing pruning, you can achieve 9 times to 13 times reduction in the size. That's a lot with the same accuracy. And when you now put it to quantization, you can reduce the size of the network by 27 times to 31 times with the same accuracy. And you can use definitely Huffman encoding to represent. And by using Huffman encoding, you can further reduce the size of the network by 35 to 49% with the same accuracy. That's a lot. So we had this 9 and this 36. This is like 71% at the minimum. So 71 times. So in the quantization, what do? You cluster the weights. The use case means clustering. You generate a code book. Code book is just like a map. We'll soon see that. You quantize the weights. Instead of making it continuous, you make it discrete. Then you retrain the code book with an iterative process. Once this is stabilized, then you can now use less number of bits to represent each of those discrete weights. Alright. So the first stage is the network pruning, and let's see what happens. Okay, the network pruning. So this is the quantization part where you do the clustering. So let's say, for instance, what's happening here. Let's say in a neural network, we have in one of the layers, taking one of the layers, we have this weight, in this weight matrix in our layers, and in doing back propagation, we have this weight matrix. So what this approach is saying is that you take the weights, and each weight is a floating point number, which means it's 32 bits. So if we take this one, this is 4 times 4, 16. These are 16 numbers, so you need 16 times 32 to be able to represent the whole of this. That's the whole of this weight. And that was the calculation they were trying to do here. 16 times 32. So you have 16 numbers and you have 32 bits for each of them. So you need 16 times 32 bits to be able to represent just this. You need the same thing to represent this, and that's a lot. But we can reduce that with, what do? You use k-means clustering. According to them, they use the k-means clustering at each of the layers. They didn't use cross layers. They just use in each layer. So you use k-means clustering. You choose your number of k's. Maybe your k is 3 or 4 or wherever. Then you cluster. I think they use 4 as their number of k here. As you can see, you have 4 blue, you have 4 orange, yeah, you have 4 greens, and the pink is not up to 4. Okay, I think they use 4. So you now pick your k as 4, then you pass this way through your k-means clustering. It clusters the numbers, and the output will now be that, okay, according to k-means clustering, all these blues should be the same, all these orange are the same, all these green are in the same cluster. So after they got in that, they now need to get the centroid of that cluster. And the centroid is like the center. So if you have like 1, 2, 3, 4, 5, 1, 2, 3, 4. So 1, 2, 3, 4, 5. What is the centroid? So the centroid is 3. So I have 2 on the right, I have 4 and 5, and so 3 is the centroid. That's what this is saying. So in their own approach to get the centroid, they add all the numbers together and divide by the k for their k-means clustering. So if you add 2.09 with 2.12, you're gonna get 4.21. Add it to 1.92, add it to 1.87, divide by 4, you're going to get 2. That's what they did. Let's do the easier one. Let's see this one, 0.09 plus 0. I'm adding the orange now. 0.09 plus 0.05, it gives us 0.14 plus minus this gives us 0 plus 0 plus 0 gives us 0 divided by 4. So this gives us 0. That's how they got 0 there. So that's how we have 0 here. Okay, so the same thing for the other one. So you have the centroid. Now once you have this centroid, so what you now do is that you now need to represent, remember we're still representing this way, you now need to find a code book to be able to represent these discrete numbers that you have here. So these numbers that we have here. So as you can see, they now did like indexing. Since you just have 4 numbers, so you have a cluster index. It's like a code book that, okay, the first number is represented by 0, the second number like memory reference. So since you have 4 numbers, you just use the memory reference. The first number mapped to 0, index 1, index 2, index 3. So all these index now, since they are just 4 numbers, you just need 2 bits to represent the index. You don't need 32 bits. They're just maximum is 4. So if you want to reference, for instance, this 2.09, you just reference this 3. That's all. And this 3 refers to 2.0. So you can see 2.09 is now mapped to 3, 2.12 mapped to 3, 1.92 mapped to 3, 1.87 mapped to 3. And the other ones, the green is mapped to 0. So 0. Minus 0.91 is mapped to 0, minus 1.03 mapped to 0, minus 1.08 mapped to 0, minus 0.98 mapped to 0. That's how you have the other one too. So you will now need to, okay, represent this one now. This is now what you need to keep in your, you just need to keep 4 of this, and you need to keep the code book. So the code book, instead of having 16 times 32, you just now need 16 times 2 bits. So that's why they got this compression rate here to be 16 times 32, 16 times 2 on this side. So since we have reduced this by 4, since we have reduced it by 4, now we now have 4 floating point number. Each of them is 32 bits, so you have 32 times 4, and that's what they did here in their calculation. That now you have now 32 times 4 there. I hope that is clear. So that's the compression rate originally divided by what we have been able to now compress. So you can compress that by 3.2. So similarly in the gradient, they use a clustering, and what they did in the gradient, they added up all the gradients, so cluster them, add them together, and give us this. So in the gradient, they didn't get the centroid, they just added the gradient together, and that reduced that to this. So you will see by then you had 0.03 plus 0.04 minus 0.02 get 0.02. So they multiply by linear rate and subtract from the centroid, and this gives them the activation map for that particular layer. So the number of computation has been reduced there. So that is essentially what is happening in this based quantization. You may want to reference our previous paper on more ways of more about pruning, how pruning is done. So it's just taken away. I think according to this paper, what they did is they set the threshold, and the threshold that any number that is below that threshold, they just prune it away. Of course, if since they use redo, anything that is 0 is automatically pruned away in the weight. You just don't need to do anything there. So that's what happened over there. And what they did is, initially before quantization, this is the way the distribution of the weight is. They experimented with 3 different kinds of weight sharing, initialization of shared weight. So They experimented with foggy, density-based, linear. I'm not too clear on that. If you're clear, you can drop a comment on that. But what I can just say is that they plot the distribution of the weights initially before quantization. And what you discover is after pruning, they did the distribution of the weight before pruning in this figure. So after pruning, they discovered that most of the weights that were pruned are in the center, and that makes sense. So where you have 0. So after pruning, the distribution of the weight is now split into two, kind of like positive, kind of like a bipolar thing, positive and negative. So that's the observation that they observed here after pruning. So because they observed that, so they now decided to so this is the discretizing. I mean discretizing. That's the word, discretizing. They make it discrete. So they make this continuous figure here now to be discrete. So they made this discrete and this discrete. And now the first blue is what gave them this. The other blue is what gave them this part. As you can see, the value is still here. So after discretizing that, they have this others. So then they now did the Huffman encoding, which now uses the more bits for the less frequent one, and use less bits for the more frequent one. So as you can see here, the highest here is 11 bar here, and you see it has lesser bits here, and the lowest here is like 1, and it has more bits here. So they did a count, and they now use Huffman encoding to represent the more bits with to represent where you have more frequent bits with less, where you have more frequent weight with less bits, and where you have less frequent weight with more bits, just to make it efficient in compressing. So experiment showed that Huffman coding this non-uniform saves at 20 to 30% of the network storage. So more common symbols are represented with fewer bits. And that's all. Very simple and an efficient technique. The rest is just experiment. They experimented on AlexNet neural network, and 2NNest and ImageNet. So on AlexNet, they experimented on LeNet 300. These are all network 300, 100, LeNet 5. They experimented on VGG 16, and they experimented. So based on their experimentation, they find all this observation consistent, that you can prune just any network, whether it's convolutional neural network or fully connected network. You can prune any one of them. So they did an ablation study. That's what this is showing. So they did an ablation study. Since they are doing pruning, quantization, and Huffman encoding, so they try to see how pruning and quantization, how it works together. So they first of all did pruning, which represent the pink, and they discovered that when they did pruning alone, they can only reduce the size to roughly here, roughly around maybe close to 10%. So anything from 10%, when they compress it less than 10, from 11, between 11 and 10%, the accuracy of the model began to drop. So they cannot, what this is showing in the blue is that they cannot prune more than 11% effectively. Once they prune more than 11%, the accuracy begins to drop. But compared to when they did pruning and quantization, which is red, you see that they can continue to even prune up to like close to like 3%. here before the accuracy begins to drop. So then when they did quantization only, which is this yellow one, they discovered that they can prune up to like I think if you check here, it is the accuracy is still the same here to like 13 thereabout, but from 11 downward, as they began to prune more, as they began to compress it more, the accuracy began to drop. This is the loss in accuracy they began to experience. So you see here that there is no loss in accuracy at all. It's just 0.0. But when you get here, this is like negative 0.5% loss in accuracy. You get here that it's like the accuracy has dropped to like less by 4.0. So the accuracy keeps dropping. So, but the point is quantization and pruning works together. So with the two, you are able to compress the network architecture further. I'm not sure what this SVD is talking about. Somebody can drop a comment on that. And so that is what all this it's all about. That's the same thing they're trying to look at here. When they quantize only, when they prune and quantize, you see how the accuracy improves on that. And they discovered that you can actually prune more with a fully connected layer as compared to conv layers. And the argument is that the convolutional layers is already optimized, since it's just by the fact that convolution is it's using shared weight in its architecture compared to fully connected layer. So because of that, you can only prune less in convolution layers as compared to fully connected layers, where you can actually prune more. So as you can see here, you see that even in the number of bits, they discovered that you can only represent the convolution layer with around 5 bits. Anything less than 5 bits, the accuracy begins to drop. But for fully connected layer, you can represent it with like 3 bits, even up to like 2 bits, before you begin to see diminishing accuracy. So that's what this is saying in the quantization, when they are quantizing and pruning. So the red represent pruned and quantized, the green represent pruned and quantized for top 1 and for top 5 respectively. So they also did comparison on quantized only and did they do anyone on they didn't do anyone on prune only. So they have on quantized only, and they did for prune and quantized, both for conv layers and FC layer, and they did for all the layers together. So that's just about that. And the same thing here, number of bit by effective weight, number of bit by effective weight. When I'm not clear what's happening here, somebody may drop a comment or what's happening here. Uniform innate, dense innate, random innate. I'm not clear what's happening here. So this is based on the different architectures, and they showed on different GPUs, CPUs, how much you are able to prune, that's what's happening on different hardware, how much you can compress. They show that, for instance, this GPU prune, you can prune on GPU for like 56 times, and they showed in the red TK1 you can prune like 3 times. Alright, I think that's about all. That is the idea of the paper. Do let us know what your comments are. Thank you for listening, and see you in the next one.